Welcome! Today, we'll be diving into LeetCode problem number 2162, minimum cost to set cooking time. This problem challenges us to find the most efficient way to set a cooking time on a microwave, minimizing the cost of button presses. We'll break down the problem, explore the different approaches, and analyze their complexities. Let's get started. In this problem, you are working with a microwave oven that allows you to set cooking time in minutes and seconds. The controls include 4 buttons, the plus and minus buttons to adjust the cooking time by 1 second, and the next and back buttons to move the cursor between digits of the time. However, there's a constraint: the cooking time cannot exceed 99 minutes and 99 seconds. The time is displayed in the format MMSS, so for instance, 70 seconds would appear as 1:10, meaning 1 minute and 10 seconds. You are provided with some key inputs: the current digit displayed on the screen, the cost of moving the cursor between digits, the cost of pressing a button, and the target time in seconds. Your goal is to determine the minimum cost required to set the desired cooking time on the microwave. To solve the problem, you need to calculate the minimum total cost to set the given cooking time. Let's look at an example. Suppose the starting digit on the microwave is 1, the cost to move the cursor is 2, the cost to press a button is 1, and the target time is 600 seconds. This translates to 10 minutes and 0 seconds, displayed as 10 o'clock. To set this time, you would first press 1 since you're already on the digit 1, and that costs 1. Then, you move the cursor to the next position, which costs 2. You press 0, which costs another 1, and repeat the process for the next digit to set the final 0. Adding up all these actions, the total cost is 6. This demonstrates the process of calculating the cost step by step to achieve the desired time. Now consider another example where the starting digit is 0, the cost to move the cursor is 1, the cost to press a button is 2, and the target time is 60 seconds. This is equivalent to 1 minute and 0 seconds, displayed as 1 o'clock. One way to set this time is to press 0, move the cursor, press 1, move the cursor again, and finally press 0. This approach gives a total cost of 8. However, there's a more efficient way. You could start by pressing 1, move the cursor, and then press 0. This reduces the total cost to 4. This highlights the importance of considering all possible ways to set the time and choosing the one that minimizes the cost. In another example, the starting digit is 9, the move cost is 4, the push cost is 3, and the target time is 120 seconds. This corresponds to 2 minutes and 0 seconds, displayed as 2 o'clock. Since the starting digit is 9, you first need to move to the digit 0, which costs 4. Then, you press 0 at a cost of 3. Next, you move to the digit 2 for another cost of 4, press 2 for 3, move to the final position for 4, and press 0 for 3. Adding all these costs gives a total of 15. This example demonstrates that if the starting digit is far from the target digits, additional movement costs can significantly increase the total cost. There are several edge cases to consider in this problem. First, when setting very small times like 5 seconds, displayed as 0:05, you'll need to handle single-digit times efficiently. For large times close to the maximum limit, such as 6039 seconds displayed as 99:99, you must ensure the solution scales well. Another case involves starting with a digit that matches part of the target time, which can save movement costs. Additionally, representing times like 70 seconds as 1:10 instead of 00:70 can be more efficient. Finally, setting times with many zeros, such as 10 o'clock or 1 o'clock, may require strategic cursor movements to minimize costs. These scenarios highlight the need for a robust approach that handles both typical and uncommon cases effectively. To approach the problem of finding the minimum cost to set a cooking time on a microwave, we start by considering a brute force method. The idea here is to exhaustively evaluate all possible cooking times, which can range from 0 to 99 minutes, or equivalently 0 to 5,940 seconds. For each valid time, we calculate the sequence of button presses required to set it and the associated cost. This involves representing the time in both minutes, seconds format and as a sequence of button presses. Then, by simulating the process of setting the time, we account for the cost of consecutive button presses, distinguishing between same button and different button costs. Throughout this process, we keep track of the minimum cost encountered. However, the drawback of this approach is its inefficiency. Since it evaluates all possibilities, including invalid ones, the computational complexity is high, making this method impractical for larger ranges of inputs. Now, we consider a more efficient method called the optimized approach, which uses targeted simulation. Instead of iterating through all possible times, we focus only on valid representations of the target cooking time. Cooking time can be expressed as a combination of minutes and seconds, where minutes range from 0 to 99 and seconds range from 0 to 59. This drastically reduces the number of cases to simulate. For each valid combination of minutes and seconds, we determine the sequence of button presses needed to set the time and calculate the associated cost. By evaluating only these valid sequences, we can track the minimum cost and return it as the solution. Importantly, this method is much more efficient than brute force, as it limits the number of simulations to a small subset of valid cases. However, careful handling of edge cases, such as leading zeros and potential time overflows, is required to ensure correctness. The key insight here is that for any target time, only a few valid button sequences need to be evaluated. An alternative approach we could consider is using dynamic programming. This method views the problem as a series of state transitions, where each state corresponds to a button press and the remaining time left to set. The transitions account for the cost of pressing the same button consecutively versus switching to a different button. By defining the states in this way, we can use dynamic programming to compute the minimum cost to reach a state where the target time is fully set. While this approach is methodical and can handle complex scenarios, its practicality is limited for this specific problem. The potential state space, which depends on the total time and number of buttons, can grow large, leading to increased computational overhead. Additionally, given the constrained input size and limited number of valid representations for this problem, dynamic programming is often overkill and less efficient than the targeted simulation approach. Ultimately, the optimized approach, or targeted simulation, is the most suitable strategy for this problem. This choice is driven by the observation that the range of valid, minutes, seconds, pairs for any target time is small, allowing us to reduce the problem to simulating just a few valid button sequences. By focusing on these sequences, we avoid the unnecessary complexity of brute force or dynamic programming. While brute force is straightforward to implement, it is computationally expensive. Dynamic programming, on the other hand, is powerful but introduces unnecessary overhead for this problem's constrained input space. The optimized approach strikes the right balance between performance and simplicity, efficiently handling edge cases like leading zeros with targeted checks. In conclusion, this method effectively addresses the problem requirements while maintaining computational efficiency, making it the clear choice for solving the minimum cost to set cooking time. In this problem, we need to determine the minimum cost required to set a cooking time on a microwave. The time is entered in the format MMSS, representing minutes and seconds, and there are specific rules and constraints we must follow. First, the total cooking time must fall between 1 and 99 minutes, inclusive. Additionally, the microwave accepts exactly 4 digits for input, which means leading zeros are necessary when required. For example, to set 1 minute and 30 seconds, you would input 0, 1, 3, 0, and for 40 seconds, 0, 0, 4, 0 is required. This leads us to the cost rules. Pressing a button has a cost. If the current button press is the same as the previous one, it costs 1, but if the button pressed is different, the cost is 2. The goal is to minimize the total cost of these button presses while adhering to the constraints. This forms the foundation of our approach to solving the problem. To solve the problem efficiently, the algorithm begins by generating all possible valid cooking times. Since cooking times range from 1 minute to 99 minutes, we convert these into a total number of seconds, ranging from 60 seconds to 5,940 seconds. For each value in this range, we calculate the corresponding MMSS format. This is done by dividing the total seconds into minutes using integer division and finding the remaining seconds using modulo. For example, 125 seconds would be converted to 2:05. It's essential to ensure that the resulting MM and SS values satisfy the microwave's constraints, where minutes must be between 0 and 99, and seconds between 0 and 59. Once we have valid times, the next step is to simulate the button presses for each time. Each valid MMSS time is converted into a 4-digit sequence, such as 1:05 becoming 0105. We then calculate the cost of entering each sequence. Starting with a cost of 0, we traverse the sequence digit by digit, adding 1 to the cost if the current digit is the same as the previous one, or 2 if it is different. This systematic approach ensures that we consistently calculate costs for all possible valid times. The next part of the algorithm involves tracking the minimum cost. We maintain a variable called min_cost to store the lowest cost encountered so far. For each valid time sequence, we calculate its cost based on the button press rules. If the calculated cost is lower than the current value of min_cost, we update min_cost to reflect the new lower value. After evaluating all valid time sequences, the algorithm concludes by returning the value of min_cost as the result. This ensures that the solution is optimal. Generating all valid times is a crucial step because the problem's constraints make it computationally feasible to evaluate every possible combination. This guarantees that no potential optimal solution is missed. By explicitly calculating the cost for each button sequence, we account for the dynamic nature of the costs, where the value depends on whether consecutive digits are the same or different. While this may seem like a brute force approach, it is efficient due to the limited range of valid times and the simplicity of the cost calculation. To further enhance the algorithm, we can introduce optimizations. One such optimization is pre-computing sequences and their costs to avoid recalculating the same values multiple times. This reduces redundant computations and improves efficiency. Additionally, we can implement an early exit condition during cost calculation. If the cumulative cost for a sequence exceeds the current min_cost, we can skip further calculations for that sequence, as it cannot lead to a better solution. In terms of data structures, the algorithm primarily relies on an array to store the 4-digit sequences for each valid time. For instance, the sequence 0105 represents 1:05. This makes it easy to traverse and calculate costs. Alongside this, a single variable, min_cost, is sufficient to track the lowest cost encountered during the process. These optimizations in data structures ensure that the algorithm is both efficient and straightforward. Finally, let's analyze the time and space complexity of the algorithm. For time complexity, generating all valid times involves iterating through the range of total seconds, which spans from 60 to 5940. This gives us 5,940 iterations, or 5940, which is linear in the number of seconds. For each valid time, we simulate button presses, which involves traversing a 4-digit sequence. This adds a constant factor of 4 per sequence. Multiplying these together, the total time complexity becomes 5940 by 4, or simply 23,760. While this may seem large, it is manageable given the problem constraints. As for space complexity, the algorithm only requires storage for the sequences and the min_cost variable. Since the sequences are processed one at a time and there's no additional data structure scaling with input size, the space complexity is 1, or constant. This makes the solution both time efficient and memory efficient, completing our analysis of the problem. This solution defines a function min_cost_setTime that calculates the minimum cost to set a desired cooking time on a microwave. The function takes 4 inputs: start at, the starting button position, move cost, the cost to move between buttons, push cost, the cost to press a button, and target seconds, the desired cooking time in seconds. The problem is solved by iterating over all possible combinations of minutes and seconds that satisfy the given target seconds. Each valid combination is converted into a 4-digit string, e.g., 0130 for 1 minute 30 seconds. For each time string, a helper function calculate_cost computes the cost of entering that time on the microwave. The calculate_cost function iterates over the digits of the time string. If the current digit is different from the previous one, it adds the movement cost, otherwise, it skips the movement cost. In either case, it adds the push cost for pressing the button. The total cost is returned. The main function keeps track of the minimum cost encountered across all valid time combinations. To ensure correctness, it validates that seconds remain in the range 0, 59, and limits minutes to a maximum of 99. Finally, the function returns the minimum cost found. This solution is efficient due to its bounded search space, 100 possible minutes, and direct computation of costs for each possibility, making it well suited for the constraints of the problem. Here, we begin implementing the solution in Java. The method minCostSetTime takes 4 parameters: start at, which represents the starting digit on the microwave keypad; moveCost, the cost of moving your finger to a different digit; pushCost, the cost of pressing a digit; and targetSeconds, the total cooking time in seconds. Inside this method, we define a helper function called calculateCost to determine the cost of entering a specific time string on the keypad. It initializes cost to 0 and uses the startAt parameter to set the initial position of the finger. As we iterate over each character in the time string, we add the moveCost whenever the current digit differs from the previous one and always add the pushCost for pressing the digit. This ensures that we calculate the total cost of entering the given time string. Next, we initialize minCost to the maximum possible value to track the minimum cost. Then, we loop through all possible combinations of minutes, from 0 to 99. For each minute value, we calculate the corresponding seconds by subtracting the total seconds accounted for by the minutes from target seconds. If the seconds are valid, that is, they fall within the range of 0 to 59, we proceed to create a formatted time string where seconds are always displayed as 2 digits. With the formatted time string in hand, we calculate its cost using the calculateCost helper method and update the minCost variable to the smaller of its current value and the newly calculated cost. This ensures that we always retain the minimum cost across all valid time combinations. Once all the minute and second combinations have been evaluated, we return the minCost as the result. This approach systematically explores all feasible time configurations while leveraging the helper function to compute the cost efficiently, ensuring the solution is both accurate and optimal. Here, we start with a basic example where the input parameters are startAt equals 1, moveCost equals 2, pushCost equals 1, and the target seconds is 61. The first step is to convert the target seconds into valid combinations of minutes and seconds. In this case, 61 seconds translates to 1 minute and 1 second, so the only valid time string we can form is 101. Next, we calculate the cost to input this time string. The traversal starts with the digit 1. Since we are already at 1, no movement is needed, so we only add the pushCost of 1. Then, for the digit 0, we move from 1 to 0, which adds the moveCost of 2 and another pushCost of 1, bringing the total to 4. Lastly, we process the digit 1 again by moving from 0 to 1, adding another moveCost of 2 and pushCost of 1, making the total cost 7. Since this is the only valid combination, the minimum cost is 7, which becomes our output. Now, let's look at another example with startAt equals 0, moveCost equals 1, pushCost equals 2, and target seconds equals 150. First, we convert 150 seconds into its possible minute-second combinations. This gives us 230, which translates to the time string 230. To calculate the cost for this string, we start at the digit 2. Since the starting position is 0, we need to move to 2, adding the moveCost of 1 and the pushCost of 2, for a total of 3. Next, we process the digit 3, moving from 2 to 3, which adds another moveCost of 1 and pushCost of 2, increasing the total to 6. Finally, for the digit 0, we move from 3 to 0, adding the same costs again for a total of 9. Since this is the only combination available, the minimum cost to input the time is 9, which we return as the output. In this edge case example, the input parameters are startAt equals 9, moveCost equals 3, pushCost equals 5, and target seconds equals 9. Here, the target seconds convert to 009, which gives us the time string 09. To calculate the cost, we start with the digit 0. Since the starting position is 9, we first move from 9 to 0, which incurs a moveCost of 3 and a pushCost of 5, bringing the total to 8. Next, we process the digit 9, moving back from 0 to 9, which adds another moveCost of 3 and pushCost of 5, making the total cost 16. With no other combinations possible, the minimum cost for this input is 16, which is returned as the result. For this case, the output is 16. This example highlights how higher movement and push costs, combined with starting at a less optimal digit, can result in a significantly higher total cost. By carefully analyzing the given parameters and calculating the cost step by step, we can systematically determine the minimum cost to input any valid cooking time. To analyze the time complexity of this solution, we start by considering the iterations over possible combinations of minutes and seconds. The outer loop iterates through all possible values of minutes, which can range from 0 to 99. This gives us 100 iterations. For each value of minutes, we determine the corresponding seconds by subtracting the total seconds used by the minutes from the target cooking time. A quick validation step ensures that seconds falls within the valid range of 0 to 59. This validation is an O1 operation since it only involves a simple check. Now, when a valid minutes seconds combination is found, we generate the time string, such as 123 or 0456. This operation depends on the length of the string, which is at most 4 characters, so it takes constant time, O1. Finally, the calculate_cost function is called to determine the cost of pressing buttons on the microwave. This function involves comparing adjacent digits in the time string, which also operates on at most 4 characters, keeping it a constant time operation. Overall, the work done for each valid time combination is O1. Now that we understand the individual steps, let's look at the overall time complexity. The outer loop runs for 100 iterations, and for each iteration, we perform constant time operations, including seconds validation, time string generation, and cost calculation. Multiplying the number of iterations by the constant work for each gives us O100, which simplifies to O1, as the number of iterations remains fixed and independent of the input size. Shifting to space complexity, the memory usage is determined by a few temporary variables such as min_cost, minutes, seconds, and the generated time_str. These variables occupy constant space, or O1. Importantly, the solution does not rely on any additional data structures, nor does it use recursive calls that might require extra memory, keeping space usage minimal. Therefore, the space complexity of this solution is O1, as there is no memory overhead that grows with the input. To highlight the efficiency of this optimized approach, let's compare it to the brute force method. A brute force solution would involve generating all possible 4-digit time strings, ranging from 0000 to 9959, and converting each to minutes and seconds. This would entail 10,000 iterations, as there are 10,000 possible strings. In contrast, our optimized approach dramatically reduces this to just 100 iterations by focusing only on valid minutes, seconds, pairs, or minutes ranges from 0 to 99. This targeted iteration eliminates unnecessary computations. Regarding best, average, and worst-case scenarios, the solution always performs the same 100 iterations, as there is no early termination. This means the time complexity remains consistent at O1 in all cases. In conclusion, the optimized solution achieves significant efficiency improvements over the brute force approach, maintaining O1 time and space complexity due to its constant number of iterations and minimal memory usage. This ensures the solution is both fast and lightweight in all scenarios. When tackling this problem, there are several common mistakes to watch out for. One frequent error is misinterpreting the 99-minute limit for cooking time. Many candidates assume that the maximum time is 99 minutes, but the problem clearly allows up to 99 minutes and 99 seconds. This subtle distinction can cause incorrect validation logic if not properly accounted for. To address this, make sure your solution handles the full range of valid times, from midnight to 99:99, and correctly converts between minutes, seconds, and button presses. Another issue involves ignoring leading zeros when calculating button presses. For example, entering 8:30 and 8:30 might seem identical for cooking time, but they require different button presses due to the leading zero. Always account for this when determining the cost. Additionally, edge cases for invalid times, such as 90 minutes and 70 seconds, are often overlooked. You need to validate that the total time doesn't exceed the 99:99 limit before proceeding with cost computation. Lastly, overcomplicating the cost calculation is another pitfall. Some solutions involve unnecessarily complex logic, which can lead to inefficiencies and bugs. Instead, focus on the two key factors, the number of button presses and whether consecutive presses are the same, as these directly impact the cost. Another challenge is failing to consider multiple valid inputs for the same time. For example, 60 seconds can be entered as 1 o'clock or simply 60, and each format may result in different costs depending on the number of button presses. To find the minimum cost, it's crucial to explore all valid input options. From an interview perspective, there are a few important insights to keep in mind. First, always demonstrate a clear understanding of the input constraints, such as the range of valid times and how to handle invalid inputs. Interviewers often test your ability to manage these edge cases. Next, optimizing for clarity is just as important as solving the problem. A clean, modular solution that separates time validation, cost calculation, and input exploration will not only make debugging easier but also leave a strong impression. Additionally, be prepared to discuss trade-offs in your approach. For instance, while brute force methods may work due to the problem's small constraints, you should be able to justify why you chose them over more optimal algorithms. Lastly, edge cases are critical. Test scenarios such as midnight, 99:99, and 59:59 to ensure your solution is robust. Mentioning these cases in an interview will demonstrate thoroughness and attention to detail. This problem is also closely related to other challenges on LeetCode, which may help you draw parallels and refine your approach. For instance, LeetCode number 121, best time to buy and sell stock, is another example of an optimization problem. Similarly, LeetCode number 134, gas station, involves handling circular constraints, which can offer insight into edge case management. LeetCode number 179, largest number, deals with number formatting and comparisons, a skill that is directly applicable when working with button presses and time conversions. Finally, LeetCode number 935, night dialer, involves dynamic programming with button presses, making it particularly relevant if you're exploring a DP-based solution here. Now, in terms of alternative approaches, brute force is the most straightforward. By enumerating all valid cooking times and computing the cost for each, you can guarantee correctness. However, this approach can be computationally expensive and lacks elegance. A greedy search strategy can improve efficiency by prioritizing fewer button presses and avoiding repeated digits, but it risks missing some valid combinations, leading to suboptimal results. For a more balanced solution, dynamic programming offers a structured way to calculate the minimum cost by leveraging state transitions. While DP is more complex to implement, it strikes a good balance between efficiency and correctness, making it a strong choice if you're comfortable with the added complexity. Great job! We covered the key insights for solving minimum cost to set cooking time. Remember to focus on edge cases and efficient computation. Thanks for watching. Be sure to like, subscribe, and explore more coding challenges. Happy coding! That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!